All right, last day of new notes. Again, IVT and squeeze theorem. Tomorrow we'll answer questions and review. I've got a limit group worksheet thing that I added this year. That'll help review things. And then review again on Monday, and then test Tuesday, Wednesday. Okay, intermediate value theorem and squeeze theorem, and they're very much related to each other. The IVT is an example of an existence theorem. Just to prep you for what's coming, there's IVT, there's EVT, and there's MVT. And later in life, later this semester, we'll learn the others, and then we'll talk about the differences and similarities. But those are all existence theorems. That means they guarantee the existence of something. So the conclusion of this theorem is something exists. So it maybe seems weird, like the conclusion isn't x equals 12. The conclusion is, yeah, there's a number that works for this scenario. Okay, so before we get to the details, let's use an example that is almost so silly, it's like, why are we including this? But this example illustrates the intermediate value theorem. Susie weighed 7 pounds at birth, age 0 years. At 17 years old, Susie weighs 137 pounds. Must there be an age at which Susie weighed 86 pounds? Good, you're all saying yes. Why? How do you know that at some point Susie weighed 86 pounds? How do you know that? Preferably without looking at the next line of the... How do you know that at some point Susie weighed 86 pounds? Like, put it in words. Don't even use calculus. Just how do you know?
The body develops.
Okay, the body develops.
You can't just go from weight to weight.
There you go. You can't just skip around. Like you gradually gain or lose weight. So you had to go through all of the weights in between 7 and 137. So somewhere in there you had to go through 86. And the magic word there is the function is continuous. So that's the calculus reason. The other reason why that's the answers that you guys were giving. Like you can't just gain 10 pounds like at once. Although I've had people debate this, like when you take a big bite of something, does that mean you immediately gain whatever amount of weight you just put in your mouth? So maybe it's not exactly continuous. Like, you know what I'm saying? Like if I could put a quarter pounder in my mouth all at once, did my weight immediately gain by 0.25 pounds? I guess so. So maybe this example isn't quite perfect, but there's no jumps usually. We thinking like it's a smooth up, and maybe there's some ups and downs. You start working out or whatever, but like it's continuous. You're going to go through all those weights. So there has to be some age where Susie weighed every weight between 7 and 137. So we don't know where it happened or when it happened, but we know that weight of 86 existed somewhere. Is 86 a special weight? Like, no, not really. What other weights are guaranteed? Well, every weight between her 7 and everything between 7 and 137. There exists a time, we don't know when, but there exists a time in Susie's life where she weighed every single weight between 7 and 137. Because it's continuous. You can't jump weights. That's the intermediate value theorem. Now we're going to say it fancy with variables and functions and things like that, but the idea is you can't get from here to here if it's a continuous function without going through every value in between. If f is continuous, okay, so we spent all day yesterday talking about continuity. So if it's continuous on some closed interval from a to b, f of a doesn't equal f of b, that would mean, like, right, if she weighs 100 pounds yesterday and 100 pounds tomorrow, this doesn't really work. Like, there's nothing in between 100 and 100. k is any number in between the y values, then there is at least one c, now we're talking x values, between the start time and the finish time, where her weight equals whatever our target value is. Right? Again, this is confusing to look at, but don't get lost in, we're just tracking her weight and she goes through every weight eventually. That's what this is trying to say. IVT guarantees that every y value between the starting y value and the ending y value has to exist somewhere between the starting and ending x values. Let's do an example, because yes, of course it does. So how do we even work this in a problem? Given that h is continuous, okay, that's super important that h is continuous. That means it qualifies for the intermediate value theorem, as opposed to, should do a discontinuous graph. If it's discontinuous, if there's a jump, well then this wouldn't qualify, because maybe that value we're asking for is in between there and it never happened because we jumped over it. Again, that can't happen for weight, so it's got to be continuous. Alright, if h is a continuous function, h represents the height of a tree, so that makes sense that would be a continuous function. It just continually grows. H is in meters, t is in years. Selected values of h are given in the table below. Explain why there must be some t at which the height of the tree is 17 meters. Okay, well first, can you convince yourself that the height of this tree was 17 meters at some point? When did it happen? Okay, before 6, after 3, between 3 and 6. So, in some sense, this is an easy question. I guess the trick is, how do I present my information that would give me all the credit on a test? Okay, well, it's an IVT problem, and IVT is, if it's continuous, then I'll give the endpoints. So I need to say that h is continuous. Don't have to say that that's given. My parenthetical remarks are not required, but I know it's continuous because you told me it was continuous. You have to include that as part of your answer, because if it wasn't continuous, like if this tree was magically hopping heights, then we wouldn't know that it was ever exactly 17. But it's continuous, and we have to say that it's continuous. Then we need to give the endpoints, or the bracket points that we're concerned with. For this one, you could give 1 and 10, because 17 is in between 0.7 and 27. But you guys narrowed it down, like you saw right away that, well, it's in between 3 and 6. So let's basically say that. H of 3 is 3.2. H of 6 is 19.3. I think I'm going to write what you said. 17 is between 3.2 and 19.3. Some people like to write it out in words because that's what their brain is thinking. Other people will just say, we'll put it in like a mathy looking way. 3.2 is less than 17 is less than 19.3. So you don't need both of those. You could say either one of those things. You're just saying that, look, 17's between 3.2 and 19.3. And then you can make your conclusion. Therefore, the 3 dots that make a triangle, that's a fancy way of saying therefore. There must be some time between the two time values, between 3 and 6, where h equals 17. some sense, the IVT could be explained to an elementary schooler, right? Like, if the tree keeps growing, it's got to pass through 17 somewhere. Here's sort of the three parts we're looking for an IVT proof or statement: continuity, endpoints, and then your conclusion. But if you don't give one of those, I can't give you full credit. And the mistakes are leaving out one of them, and the mistakes are sort of equally spread out. Sometimes people forget to say that it's continuous, so like they jump right into the heart of how they know, and like, oh, that's good stuff, but that doesn't work unless it's continuous. Sometimes people will say it's continuous, they remember that because I harp on it. They won't give any of this intermediate stuff, and they'll just say, well, it's got to be in there. You're like, well, yes, I know that it's got to be in there, and I know that you know that it's got to be in there, but you've got to give me the reason that it's in there. And then my favorite mistake is to do 1 and 2, but to like not give me the conclusion. It's like doing all of the work, but not telling me what the answer is. It's continuous. 17 is between 3 and 19. Got it. And then walking away. Well, you're almost there. You've got to make the conclusion that, yes, there is some time where that happens. So, I don't know. I feel like it's a little bit like continuity. Like, conceptually, pretty easy. Technically, you've got to make sure you follow the steps to convince me that it works. Questions? Okay, that was a table. This one's an equation. Explain why there must be a value of C between 0 and 3 such that G of C is -1. Well, the first statement is always continuous. G of X is continuous. This isn't going to work unless G is continuous. But how do you know that that equation is continuous? I haven't really talked about this. You know what we call that kind of equation? Fancy word for it, starts with a P. Careful, x squared would be a parabola, but x cubed would not be a parabola. You're on the right track, though. It's a polynomial. And polynomials are always continuous. So, it's a polynomial, therefore it's continuous.
You have to write that, or can you just say it's continuous?
You would need to write, you would need to say that it's a polynomial. There we go. You would not need to say that it's always continuous. We'll know that. But I need to know, how did you know that it was continuous? You knew it was continuous because it's a polynomial. Okay, part 2 was the endpoints. So on the previous one, we just looked at a table and got our endpoints. How do I know what to use for my endpoints on this one? It gives you them, 0 and 3. So let's find G of 0, and let's find G of 3. And I'm assuming that for this to work, that -1 is going to be in between whatever those answers are. But let's see. G of 0, that's an easy one. That's -2. G of 3 takes a little bit more work. See, 18 plus 3 is 21, minus 2 is 19. Yeah. Again, we have to be careful about what we show. Maybe you're convinced already because you're like, yeah, look, -1 is in between there, so yeah, it works. Yes, but you have to say all of that stuff. So the short way would just be to say that -2 is less than -1 is less than 19. Right, you're telling me that -1 is in between the end values. So now I can conclude, I mean, my conclusion, they basically gave it to me already. There is a C between 0 and 3 where G of C equals -1, because -1 is in between the two y values. Say it's continuous, give the n values, and then state the conclusion. I guess there's another slight parallel with continuity, is that it's 3 steps. Continuous, n values, conclusion. Part B, find the value where it equals -1. Okay, so this isn't really part of the IVT, but it's usually the follow-up question is, you prove that somewhere it's equal to -1. Let's figure out where this function is equal to -1. Like, oh, not so great on my cubics here. Where did that come from? You're right. How'd you know?
Because there's, when you multiply everything by 1, there's -3 but +2. Like there's 2 positives.
So basically kind of a guess and check. You plugged in 1 and it worked. That's fine. Usually we're not going to give you one that's this complicated. 1 works. Let me show some more algebra. But 1 works, so that's fine if you just said x equals 1, because I checked it. Let's see, I can factor by grouping on this guy. X squared times x minus 1 plus 1 times x minus 1. And then if x minus 1 equals 0, then x equals 1. So yes, you're right, and if you can get there, sometimes they're easy enough, the equations are easy, you can just figure them out. Other times, it takes a little more work. And sure enough, 1 is in between 0 and 3. So if we were guessing and checking, we would only be guessing and checking between 0 and 3, because that's the only answer we were allowed to get there. Yes. Oh, I guess I should have. But then I get x squared equals -1, and now I'm into imaginary, so ugh. But yes, you're right, I should have to see if there was another solution that would have worked. Intermediate value theorem doesn't guarantee only 1, it guarantees at least 1. Occasionally there's more than 1. Especially if you think about the weight. Like a tree, it might be harder, but the weight, so as a kid you're just gaining weight. Once you get to be an adult, trust me, sometimes your weight does this, right? Hopefully it doesn't like go up forever, that'd be bad. But if we ask, where does the weight equal 175? Well, if all you have are those 2 points, it happens somewhere in there. But goodness, it might have happened 3 or 4 times. School started and you couldn't work out as much, and then summer hit and you could, run more often. This is my own story I'm telling here. All right, squeeze theorem, aka sandwich theorem. Laura?
So there's nothing in words that we have to say for that second class, right?
Back up here.
For B.
So I said it in words on the first example. Here I use this to say it. If you wanted to use words, because it makes more sense to just say.
No, I meant for B for the next one. You don't have to use any.
No.
Okay.
Because this isn't an IVT problem. This is just figure out what makes it -1. So we don't have to be as formal. Okay, I've been trying to think of an example for a squeeze theorem before we get to the craziness here. to illustrate it before we get to the details and the technical stuff. Here we go. Let's flip it over. I'd like to use your names, but I don't know who scores what, and I don't want to put anybody on the spot. So let's say Mr. Wolf always scores higher than, I don't want to pick a teacher. What teacher do you want to say I'm always scoring better than? Pick on Evan's mom, but do it? Okay. Always scores higher than Mrs. Morris. But Mr. Wolf always scores lower than than Ryder? Okay. I was going to go for another teacher, but we'll use Ryder. Okay. Ryder always beats me on every test. So for some reason, for whatever reason, we know that Ryder always scores better than me, but I always score better than Mrs. Morris. On the Unit 4 test, Mrs. Morris made what did she make on that test? Evan, you want to tell us what she made on that test? Just give me a number.
60.
Ooh, that's going to be rough for the rest of my example. I'm going to give her an 85. Ms. Morris made an 85. On the Unit 4 test, Ryder made an 85. Therefore, on the Unit 4 test, Mr. Wolf made... Okay, so I'm always better than Miss Morris, always less than Ryder. They both made an 85. What did I make? I had to make an 80. I guess I should have said less than or equal to here. I had to make an 85. My grade got squeezed in between Ryder's grade and Miss Morris's grade. Now, we're going to get a lot fancier stuff than this, but that's the squeeze theorem, sometimes called the sandwich theorem, because I got sandwiched between Miss Morris's grade and Ryder's grade. And if they both went to 85 and I'm stuck in between them, I guess I got an 85 as well. That's the squeeze theorem. Now, let's put some technical, fancy-looking symbols on it, but if two things squeeze together and another guy is always in between, then he's got to match whatever the other two are. All right, if f is continuous, here we go with continuous again, and the graph of f of x lies between, here's the squeeze part of this, f is going to get squeezed. So f is, or sandwiched in between g and h for all x's. This, except possibly at c itself, this is kind of weird. We're not really going to worry about that. If the limit for g equals L, and the limit for h equals L, then the limit for f has to equal L. Let's turn it over and draw that picture. Draw another picture here. So we said it's always between g and h. G, F, and H. So here's G, here's H, don't cross, there's H. If F is always between them, then who knows, it might be doing crazy stuff, but right there at that spot, it gets squeezed. That's That's the squeeze theorem, or the sandwich theorem. If G and H go to the same thing, and F is between them, then F has to go to that as well. It gets squeezed in there, or sandwiched in there. It makes sense. I don't know, it's probably not good for calculus teachers to just say, it makes sense. It's obvious, right? If our function always lies between two other functions, those two other functions have the same limit value, then the function that's in between them has got to be the same. Okay, enough trying to explain what I think is clear. If f of x is not explicitly given, but it is known that f is continuous, the graph of f lies between x minus 2 and negative x, find the limit as x approaches negative 1 of f. Okay, well this seems weird at first maybe, because you're like, well, I don't have an f to plug it into, so I don't know what f is doing. Well, let's check g and let's check h. So limit as x approaches 1 of g, and the limit as x approaches 1 of h. And if those are the same thing and f is between there, then f will have to have the same limit. If those aren't the same thing, well then that'll be answer D. We don't have enough information here. So for g, 1 minus 2 is negative 1. For h, the limit's negative 1. So f has to be between negative 1 and negative 1. So I guess the answer is negative 1 because there's nowhere else it could be. It got squeezed in there. Question 2. If h is continuous, and it is known that the graph of h lies between the graphs of f and g, here we go again, find the limit as x approaches 2 of h of x. This is kind of the same problem. I need to plug it in. I need to check f and check g. If they go to the same thing, then I've got my answer. If they don't go to the same thing, then I don't know what it is. So let's check. Where are we? At 2. So we'll check f. We'll check g. And if we get the same answer, we're good. If we don't know anything. Sine of 2 pi over 12 plus 5. Sine of pi over 6. Pre-cal all-stars. 1/2. So that's 5.5 or 5.5. And then let's check the other one. Let's see, 2 squared is 4. 4 over 4 plus 1 over, or no, plus 2 over 4 plus 4. So 1 plus 4 is 5, plus 1/2 is 5.5. So that means the limit as x approaches 2 of h of x has to be 5.5. It's always between f and g. They're both 5.5. So he gets squeezed or sandwiched to 5.5. I don't know. Probably spent way too long talking about squeeze theorem. One function's in between the other two, and the other two get squeezed. No place for it to go. All right. Today's assignment is the last non-review worksheet, I guess we'll call it. IVT and squeeze theorem, worksheet 5. Just read carefully. When you hit the explain, make sure you give me the 3-step explanation for IVT. But other than that, other than the technical stuff, you probably could have answered the rest of it before we even did notes, right? Because it's got to go through every value, or if it gets squeezed, it's got to hit that value. So IVT and squeeze, not too difficult to think about.
If we
Hopefully.
write it down as explanation, could we just like say IVT